Welcome back to Finite Element Methods. So this is class number 26, I believe. Before I get into the main part of the lecture, though, I want to discuss a couple of homework problems from homework 8. So for homework 8, we're looking at a mixed method for the Stokes problem. So remember that we say that a pair of finite element spaces XH and QH are or form an inf-sup stable pair if the following condition holds for those spaces XH and QH. For all QH in QH, then the supremum of this quotient is bigger than beta prime times the norm of QH in the L2 norm. Uh, So I've introduced a beta prime here because normally we use beta for the inf-sup condition for the infinite dimensional spaces Q and X. So that beta that you can compute really only depends on the size of the domain and the structure of the domain. But this beta prime might be different than that. So just to emphasize, this beta prime should be completely independent of H, but it should be somehow dependent on the structure of the finite dimensional spaces that we're dealing with. U and P solve the weak solution for the Stokes problem, so they solve this set of equations. And our Galerkin approximation UH-PH satisfies this finite dimensional problem. So the idea in problem 2 was we're trying to figure out a way to prove error estimates for our Stokes problem. And we showed and talked about last time why this is such a difficult issue in general. And so we came up with this alternate strategy, which is it can be found in any good finite element book, which covers the Stokes problem and its Galerkin approximation. The idea is to formulate this B bilinear form. It turns out this bilinear form isn't necessarily symmetric. If I interchange phi and psi, I don't get the same thing. So, in fact, it's definitely not symmetric. However, it is bilinear, and it's easy to show that it's continuous, that it satisfies some inequality like this for some constant. It's also pretty easy to show that an orthogonality condition holds of this type. I'm going to remind you, or at least maybe show you if you've never seen it, how I can add or subtract two um, elements together for these product spaces. So this space phi and phi h are both product spaces. So how do we add things together in those product spaces? Well, you just add them together in a kind of um, vectorized way. So that's quite easy to do. So A, B, and C turn out to be fairly straightforward. You get this Galerkin orthogonality type of statement. Now B is not symmetric, but it's you still get this Galerkin orthogonality without any trouble. All right, so the main difficulty then is proving this condition, this inf-sup condition involving B. So I changed around uh my hints. So this part D was supposed to be a hint, and then I gave another hint here below in part E. And so if I can prove part D and I can use this hint, then I should be able to establish this. So I changed this hint and I changed effectively this hint here. And so what I want to do then is show you how to prove D and then show you how D is used to prove E using this hint. Okay, so here's that solution. I've already uploaded this onto Canvas. So if you're interested to see how this works, have a look at that. And what I want you guys to do, obviously, is go through all these details and make sure that everything makes sense. So B, this bilinear form capital B is defined in this way. It's kind of strange, kind of weird, but it turns out this is exactly what we need to get the identity that we're looking for. If I put a minus sign here in order to try to symmetrize this thing, it turns out it doesn't quite work. So this is exactly what I want, exactly this form here. And it doesn't necessarily make sense until you use it and try to make sense of it. The bilinearity, as I said, fairly straightforward, but I just threw in a quick check of that here. It's not symmetric, as I said. If I interchange phi and psi, I don't get um, the uh, the original thing back, so it's not symmetric. Continuity turns out to be fairly straightforward and fairly easy. Now, one thing I did want to point out is when I'm doing continuity, I stated two different norms uh, on the space phi, and there are two equivalent norms that one can use. And what I've done is I've used those norm equivalences here and here. So check those out if you're interested. Um, Now, let's see, orthogonality also pretty straightforward, I think. Um, and oh, I did want to say, how do we add elements together from this space? So if I have two elements like this, actually there's four elements here. But let's examine these two elements for I equals 1 and 2. Alpha phi 1 plus beta phi 2. Well, all I do is I add the first components in a sort of vectorized sense, and I add the second components together in a vectorized sense. In fact, well, I really make a linear combination of the first components and a linear combination of the second components. That's how these linear combinations are defined. That's how these scalar linear combinations can be computed. Right. So orthogonality, as I said, follows pretty straightforwardly. Now I want to use the hint to prove part D. So in part D, what am I just trying to show? I'm trying to show that there's some element ZH that such that this holds for two. So we're given RH, and I want to show that there exists a ZH such that the norm, the H1 seminorm of ZH is equivalent to the RH, the L2 norm of RH. Okay, the H1 seminorm of ZH is equivalent to the L2 norm of RH. So that's exactly what I have, an equivalent statement here. So that's what I want to prove. So here's how I do it. I've got to use somewhere along the lines the inf sup condition. So what does the inf sup condition say for our two spaces? It says if you give me an RH in QH, then this sort of inequality can hold. Now, actually, I'm using the inf sup stable, the inf sup condition for minus RH. Is that legal? Yes. If RH is an element of QH, then minus RH is also. And so the inf sup condition says this in that case, except probably need to add here that WH is not equal to 0. Okay, so in that case, everything is straightforward. There's the inf sup condition. Now, by the Riesz representation theorem, there exists a unique ZH in XH that solves this problem. The question is, why is that true? We actually discussed this a little bit last time, and the reason is because this object over here is a linear functional. It forms it's a for every given RH, it's a linear functional for objects from XH. So I could define this like this. I could say, well, this is just going to be some linear functional. Okay, I could define that linear functional that way. But in order to use the Riesz representation theorem, I need to show that it's bounded. It has to be a bounded linear functional. Not hard to show that at all. All right, so Riesz representation guarantees the existence of that. The first thing we're going to do now is plug this into um, this soup inequality that we just were playing around with. Well, if I do that, let's see what we get. Well, this object appeared in the numerator in my quotient here, and I can now replace that with the AZHWH because of this inequality or of this equality here. Now let's look at this object here. What is this object? This object is actually just the H1 seminorm of ZH. And in fact, I can prove this fairly easily. So how can we prove this? Well, first notice, let's take this quotient here. And by the Cauchy-Schwarz inequality, it's less than or equal to ZH H1 seminorm, WH H1 seminorm. But there's an H1 seminorm on the bottom, so I get cancellation. This says that this quotient is always less than that norm. Okay, now if I take the supremum of all of these numbers, this forms, first of all, this object forms an upper bound for these objects, and the supremum is the least upper bound. So any other upper bound has to be greater than the least upper bound, right? And so I definitely have this. But notice that if I take WH and I substitute in ZH for that, I precisely get the H1 seminorm of ZH. That's because on the top I have the H1 seminorm squared. But that says that the supremum of those numbers has to be greater than this, okay? Because this is just one of the possible numbers, and this is the least upper bound. The least upper bound is greater than any of the possible numbers. So that says I have this supremum being bigger than this and the supremum being less than that. Well, that must mean that it's exactly equal to that. Okay, so what did we use there? We used that precisely at this location here. So this guy here is the H1 seminorm of ZH. And that says it's greater than RH times a constant right here. So that gives me one of the inequalities that I'm searching for in the equivalence. How do I get the other inequality of the equivalence? Let's plug in into our equation 2.d.1. Okay, that's the existence of that ZH through Riesz representation theorem. Plug in for WH, set that equal to ZH. And then I get H1 seminorm squared. That's equal to the right-hand side. Use Cauchy-Schwarz inequality. This guy here, it's pretty easy to show that when I apply Cauchy-Schwarz, it's going to be the L2 norm of this object, but the L2 norm of that object is less than or equal to D times the H1 seminorm of ZH. We've shown that in one or two other locations. So that gives the upper bound. Because of cancellation, I can divide one of those away, and so I get this. So that is part D. The question is, where does that get used in part E? Okay, so it turns out why did I change the problem? The reason is because the old way of doing it yielded a pathway for the solution of the problem, but it was a lot harder than what I'm showing you here. So this way is a lot easier. Uh, I discovered that through a solution that another person showed me a long, long time ago, and I kind of lost track of it. But his solution was much, much more elegant. All right, so now we want to show that weird um, inf soup condition involving B, okay, capital B. So we're going to try to show that the supremum of these objects here taken over, it's a little typo here, taken over psi h in xh, we want to show that that's bigger than some constant times the norm, the L2 norm of, let's see, is it the L2? No, it's going to be the, well, gosh, let me go back and see what it was that we're trying to show here. Here we go. Yeah, not the L2 norm, but the phi norm of this guy here. So we're souping over the second variable, okay? And we want to show that that's bigger than a constant times the norm of the first variable. That's where we're heading. So what I'm going to do, the way I'm going to do this is if I could show, remember I'm going to end up taking a supremum of this guy. If I can pick a particular element out of thin air, then if I can show that for a particular element that this is bigger than the ultimate object that I want to show on the left hand side or on the right hand side, if I take the supremum of that, then I'll be guaranteed that that inequality will still hold. So what I'm going to do is let the first variable be entirely random. Okay, let it be arbitrary. Now that's given with a velocity and a pressure. So now I'm going to tell you how to pick this second thing. This is the thing which we would normally be taking the supremum of. I'm going to find a lower bound for this, and then when I take the supremum, I'll be guaranteed that the lower bound still holds. So for this object, I'm going to take WH, which is the same as here, and a pressure of 2RH was the same as here, but to that WH, I'm going to add ZH, where ZH is as in the last problem. Okay, part D. All right, so then here's how it works. All I'm going to do is evaluate this quotient. If I evaluate this quotient, then I just straightforwardly write down these three terms in this definition of B, which is here. Now, both A and B are bilinear, and so these three terms turn into something like five terms. Okay, the first one is going to be the H1 seminorm squared of WH. The second one is AWHZ. That should be not ZW, but ZH. There we go. And this one, WHRH. Second one is going to be ZHRH, both with minus signs, plus 2. I'm going to pull that 2 out. Again, bilinearity, WHRH. Okay, so everything looks good. Now, by the definition of this guy, right, by the definition of that guy, that's equal to, okay, according to 2.D.1, what did we say this is equal to? Well, the first thing I can do is swap these two because this is a symmetric object. So this is going to be equal to this object right here is equal to minus B. It was, let's see, WH RH. Nope, no vector on the R. Okay. Now I have another one of those lying around, namely this guy. It's exactly the same term. This one's different. And of course, this one's different, has a different coefficient. But this one and this one give minus 2 and a plus 2. Those cancel each other. Okay, so I've eliminated that one. What about this? I'm going to use I'm going to use 2.1.1 to convert this to the A bilinear form. So what would this one be equal to? This guy here would be equal to A ZH ZH. That one equals minus B ZH RH. Okay, so this guy is equal to that. So there's where I've placed that. But this is equal to ZH norm squared, right? Or the semi-norm squared of ZH. But we said that has a lower bound, which is going to be beta prime. Of course, this is semi-norm squared, so it's going to be beta prime squared RH L2 norm squared. Okay? Now I can look at these two coefficients. Okay. I'm going to use the smaller of the two coefficients, and that gives me something still smaller. And the smaller of those two coefficients, now those two coefficients are the same. I can pull that coefficient out. And all this on the top um, is just going to be phi or psi h uh, phi norm squared. Let's see, have I been? I guess I started off using arrows. Let's just be consistent here. Probably shouldn't have used arrows for that guy, but okay. In any case, there's a norm squared on the top and a norm on the bottom. And so the norm squared, one of the norms on the top cancels with the norm on the bottom just to leave the norm of psi h on the top. Of course, I still have my coefficients, right, here, which is the min of 1 and beta prime squared. Now, I showed this for a particular, or for a particular choice of, let's see, did I do that right? I did that wrong. Let's see. Let's see. I've got a. Okay, so this one is. Oh, okay. So I still have an error here. I didn't see that error. So the problem is I've got this guy on the bottom, and I need something which is going to cancel with that norm on the top. So how do I do that? So that's not exactly what I have. What I have is this. Didn't realize that before. All right, so there's a way, I'm missing one step here. And I'm gonna fill that in offline. Let's see, is that, I think maybe that's not the way. Let's see here. Yeah, I have to, I, I don't see it right now. I was canceling something that doesn't cancel, but I have that solution offline. So I need to fix this. Okay. Okay, that's a slight bummer because I thought I had it, but um, I'll correct that and get that fixed. So I hope you see what I have on the top is not quite going to cancel with the thing on the bottom. I have to do um, a little bit of trickery, a little bit of a minor calculation. So I'll fix that up and I'll push that on online. So we'll almost have it. If I did have, if I did get this object on the other side like I was looking for, then I could take the supremum over objects which look like that. Um, but it doesn't quite work out. All right, so I'll correct that and then I'll upload that. I'm sure it's a minor thing, but you don't want to see the steam coming out of my ears as I try to fix this up. So I'll do that offline and I'll push it onto Canvas when I get the solution. What I do want to do is talk about the last subject of the course before we call it quits here. And so the last topic is what's called a posteriori error estimates. I thought about doing a lot of different things, and I just kept coming back to the fact that this is an important topic that most people don't see it, but most people in in applied mathematics should see. So I'm going to try to get through this. I had hoped to get through it today, but that doesn't look like it's going to happen. So we'll um, we'll have to conclude with one more lecture, but it doesn't look like it'll be all that much uh, in addition to what I'm going to talk about today. So maybe if we had another 20 or 30 minutes, we could finish it up. In any case, what's the problem here? So the problem with a posteriori error estimates is we want to know how good of a solution we've computed with our finite element approximation. So is there some way of being able to tell how good of a solution we have? We have what are called the a priori error estimates. That's the type of error estimates we've done all along. And so that involves saying something like the difference between the solution and the finite element approximation in some norm, let's say like L2, is less than some constant times h squared, let's say, times the seminorm, h2 seminorm of u. So is this useful? Well, this tells us if, if we're talking about a particular solution, that guy's fixed for our problem. The constant is fixed, and so this tells us that as we make h smaller and smaller, then the error should go down like h squared. So it's useful, but it doesn't give us a computable estimate of the error, the size of the error. So what we're after today is some way of looking at this object and coming up with an object on the left-hand side, which is an error which is computable, or at least almost computable. So this is not computable because we don't know what the true solution is. Of course, we know what this is. We don't know that, but this part here is not computable. We want to show that this is less than an object on the right-hand side, which is completely computable. That's the idea of a posteriori error estimates. So we're going to consider the standard problem in this case. This can be done for other types of problems as well, like the biharmonic equation, for Stokes equation, for lots of different things. We're going to use the Poisson problem to examine. So we're looking for the true solution minus Laplacian of u is equal to f with u equals 0 on the boundary. Of course, we know how to get our finite element approximation. We create a finite dimensional subspace of H01. And usually we're going to use the piecewise polynomials of degree R, which are globally continuous. So we're looking for a UH and VH that satisfies this equation for every test function, which is also in the finite dimensional space VH, the finite element space. So this is the standard Galerkin approximation for our weak problem, right? So our weak problem is, of course, stated very similarly. The A bilinear form is just going to be gradient U, gradient V in the L2 inner product. And of course, the great thing about this problem is we have this rock solid fundamental Galerkin orthogonality condition for us. And that's easily gotten. If we switch this test function to the subspace, VH, then we can simply subtract these two solutions and we get this automatically. This is the error, and it's saying that the error is orthogonal to anything in the finite dimensional subspace in this A bilinear form. Okay, so now we need a few definitions to make our a posteriori error estimates go. So we'll start off with the usual constructions. Let TH be a conforming triangulation of a polygonal domain omega. So I just want to remind you, because it's going to become important for what we're going to do, that each triangle in our triangulation is considered an open set by our convention. That was a convention that we chose at the very beginning of this course. You can also do this differently and assume that each triangle is a closed set. You just kind of have to pick one convention and go with it. Now we're going to define what's called the interior edge set, gamma sub h. It's going to be the set of all edges such that an edge is considered the intersection of two triangles when I close them. Okay, remember our triangles are open by convention, so we need to take the closure of them. So here's one example. I might have a triangle on one side and a triangle on another side. So K1, K2. If I take the closure of those and then I take the intersection, that gives me an edge. So the edge is right here. Now, an edge is character. Now, you can have two triangles that have a non-empty intersection which don't share an edge. For example, these two triangles also share an edge, right? Or sorry, also have a non-empty intersection. Namely, they have a non-empty intersection at a point. So what's the difference between a point and an edge? Well, to get a full edge, what we need is whenever we get that intersection, we need to know that its one-dimensional Lebesgue measure is strictly positive. In this case, the one-dimensional Lebesgue measure is not positive. This has measure 0. But what about this guy? This one has a one-dimensional measure which is strictly positive. And so that would be considered a bona fide edge. Okay? So that's the set of all interior edges. This doesn't grab any of the edges on the boundary. Okay, there's no way using this definition that we get that. There are other ways you can include the boundary edges if you want them, but for now we don't need to worry about them. So this is the set of all interior edges. Suppose that we have a triangulation as above. For every k in that triangulation, we're going to define the omega k set. What is the omega k set? It's going to be the union of the closures of k prime. Okay, so it's going to be the union of a bunch of closed triangles such that we have a triangle in our partition, in our triangulation, with the property that, okay, so this is our original set that we want to consider, and it must have a non-empty positive measure intersection with k, okay? Or it could be, or k prime could be actually equal to k. So they have to intersect at an edge, which is non-trivial, or k prime has to be equal to k. So what's the picture of this set? So if here's my triangle k, and we're looking for all the triangles, okay, neighboring, these three neighbor triangles share a non-trivial edge with this triangle. So this triangle would go into the union. This triangle would also go into the union, and this triangle would go into the union. And then finally, if k prime is equal to k itself, it'll go into the union. So this is what this set looks like. Okay, that's called the omega k set. We also have, so this is kind of like a way of enlarging the size of k in an important way. Okay, that's the omega k set. We can also enlarge the size of E in an important way. For each edge in the edge set, interior edge set, we're looking for the union of triangles, k prime, actually the closure of k prime, such that k prime is in the triangulation, and this edge is a subset of k prime closure. So let's look at this case here. So here's the edge I want to talk about. And I have a k prime over here. Okay, take the closure of that. And is this an edge which is contained inside that closure? Yes, so this guy goes into the union. What about this guy? Let's set K prime equal to this triangle over here. If I take its closure, is the edge a subset of that closure? And the answer is yes. So this one also goes into the union. So this WE set or mega E set looks like this for this edge. Okay. Now, of course, the mesh is bigger than this, right? The mesh goes on and on in all directions. But for every edge, this guy only has two triangles in it. For every triangle, this guy has one, two, three, four triangles in that. So, and I believe you can show, it seems like it's quite self-evident actually, that since this triangle has three sides, then it's going to be the union of four triangles itself, and then it's three neighboring triangles sharing a full edge. What about this? This is always going to have two triangles in it, right? So two triangles that share a full edge uh, with each other are going to be in that edge set. Okay, so those are expanded sets that we need. We're going to need a few more as well. Suppose that ZJ is a node on an interior edge or an interior vertex. Okay, so we had a name for those guys. That was this nodal set here, N0R. This is a script N. So I'm going to define WJ or W subscript ZJ. Okay, so that's that node. It's going to be the union of all triangles, or actually the union of the closures of triangles that are in the mesh or in our triangulation, and such that that node that we're interested in is actually a subset of that triangle or the closure of that triangle. Okay, so this actually is another way of just generating the supports of our basis elements. So um, let's see if we can think about that with a drawing. So let's suppose, forget about this larger picture, but suppose that this is the node we're talking about. Then we're looking for triangles such that when we take their closure, this node is in that triangle. Well, if it's a vertex node, then it's going to be this one, this one, this one, this one, this one, and that one. Those six triangles. If it's an edge midpoint node, then it's only going to be these two that appear in the union, and it's going to be a closed set. Okay, so that's really just the same as the support set for the jth basis function. It's really the same thing. Now it turns out that's not good enough for our purposes. We're going to need an expanded set called the k tilde omega tilde k set. That's going to be the union of all um, omega j's such that zj is in the closure of k. So it's much easier if I draw a picture. Here's my set, here's my triangle k. This is defined for each k in the triangulation. What you do is you take all the nodes that are in this set k. There could be even some interior nodes if you have more exotic, but they don't really contribute anything. It's really the ones that are on the vertices or on the edges. And then I'm just going to look at taking the union of all those supports of the triangles for those basis functions. So first of all, let's look at the basis function of this guy. So it's going to be 1 here and 0 everywhere else. The support are those two triangles. Look at the basis element for this one. The support is all those triangles. Support is those two triangles. These six triangles are in the support of this one. This one has two triangles in its support, and this one again, six. Okay, so I have to union all these triangles together, and that gives me this big set of elements surrounding K. This is what we call omega tilde K. You can do the same thing for edge sets. What we're doing in that case is we're just taking the vertices which are, or sorry, the nodes that are in a particular edge. Okay, so you're given an edge, it has a number of vertices in it, and then you just take the unions of all the supports for the nodes or for the basis functions relative to those nodes. So this basis function is going to have five triangle is in its support, so throw that into the union. This one has um, two triangles, but of course those are already covered in this guy, so I don't really add anything there. And then I have this node here, and its support has these 6 elements. So I'm going to throw that in the union as well. Now, here's why I made all these definitions. These are going to be useful to me in this proof that I'm going to do in a moment. I'm going to do a construction next for what's called the Clément interpolant. The Clément interpolant. Why do I need a new interpolant? Well, I need an interpolant for functions that are not necessarily continuous. So let's take a function that's in L1. Okay. First of all, let's let TH be a triangulation of a polygonal domain. And now consider a function in L1. A function in L1 is not necessarily a bounded function. It's not a continuous function. Doesn't necessarily have point values, right? But I still want to find out how I can interpolate functions or get an interpolant of this function. I can't get an interpolant in the usual sense, but I can generate a function which approximates this function, which is exactly what an interpolant does. So we usually call this interpolant a quasi-interpolant. So what I'm going to do is take a point in the node set, the nodal set. So grab a node. So remember, a node can either be a vertex node or an edge node, or it could even be an interior node, but we really haven't looked at those cases too much. So just think about a vertex or an edge node. So grab a node, and what we're going to do is, remember we have the support of the associated basis function phi j, right? So this is equals nothing more than the support of phi j. Right? So what I'm going to do is I'm going to call this one this 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 object VJ bar. VJ bar. VJ bar. Remember, an overbar usually denotes something called an average. And so this is exactly what this is. This is an average of this function over that set omega j, the support of phi j. Why is it an average? It's an average because you're dividing by the size of the domain over which you're taking the average. Okay, so this is what's called the average. The average could be positive or negative. It has a sign associated to it. Okay, positive or negative according to the structure of this function v. Now we want to define this operator IH. It's going to take any function that's an L1 function. This is defined for an L1 function. All that we need to know is that v is integrable. If it's integrable, we can calculate that object. So it's going to take any integrable function and it's going to push it, it's going to kind of mash it into this set, this finite dimensional subspace of the piecewise polynomials of degree r that are 0 on the boundary. How does it do this? Well, it takes the averages over these supports and then it multiplies that value times the basis function. Okay, remember, if I make a linear combination of the basis functions for this space, then the object that I get has to be in that space. This gives me what's called the Clément quasi-interpolant. Clément quasi-interpolant. Again, these are just the basis elements for this in this Lagrange nodal basis set. The basis elements for this finite dimensional space, this finite element space. Here, I'm just recalling the notation that we used way back in class number 9 or 10. And here we had all these superscripts and subscripts. I can just drop those and just use this single subscript here. That's all I'm doing. I'm saying this is the same function. I've just dropped all the addressing on it. All right, so this is what we call the Clément quasi-interpolant. Clément quasi-interpolant. It's not an interpolant in the usual sense. An interpolant usually means that you're using the point values and then you're connecting them them up using a piecewise linear or piecewise quadratic or a spline or something like that. So this is not an interpolant, it's a quasi-interpolant. Let TH be a shape regular triangulation. So what does shape regular mean? Well, I'll remind you a little bit later. A shape regular triangulation of the polygonal domain omega in R2. Where you're doing everything in R2, you can push these ideas into R3, but it's requires a little bit more machinery that we're not going to worry about. Now, if V is an H01, we just said we're going to define the Clément interpolant for L1 functions. And the question is, if I take a function from this space, is it integrable? Yeah, actually it's square integrable. So it's more than integrable. And its first derivative is also square integrable, right? It's first weak derivative. And it has zero boundary conditions. Right? So this definitely is an L1. This function is definitely in L1 if we're talking about a finite domain. And I can measure its error, okay? The difference between V and its interpolant. Okay, so we're using the Clément interpolant from above. The difference between V and its Clément interpolant is what we call the Clément error. We're going to measure that in the L2 norm over a triangle, okay, in our mesh. That's less than C times a constant, or sorry, a constant times HK. That's the size of the triangle K, right? It's the diameter of the. In effect, this is just you can either call it the diameter of the triangle, or you can just let it be the size of the largest edge. Okay, the largest edge that you measure. HK times the H1 seminorm of V. But here's where we need those special definitions that we just made. It's not over omega K. It's not even over K. It's over omega tilde K, which is this big set here. So even though we're really only interpolating this function on this set, we need the we need the size of the H1 norm of the original function on this much bigger set. Okay, on all of this omega k tilde. So this is what you give up when you use this averaging operator, this Clément interpolant. You need to measure the size of the error with this bigger set. Okay, our normal errors that we generated last time with Lagrange nodal interpolant, those worked for H2 functions, and we only had the H2 seminorm on the set K. Here we can't do that. But the good news is we can define this interpolant for functions that are not even continuous. So these functions here, H01, are not even continuous according to what we know about Sobolev space functions. These functions here are not necessarily continuous. They can be unbounded even. Okay, so that's the error of the Clément interpolant on the triangle. We can also measure the error on an edge, the error on an edge. And so this error works out to be less than a constant times the length of that edge. So HE simply means the one-dimensional measure of the edge. So that's just the length of that edge. Okay. Raised to the 1/2 power times the H1 seminorm of V. But again, it's not over just the set E. You have to expand it to omega E tilde. So if we're talking about this particular edge right here, then omega E tilde is all of these triangles and that surround that edge. It's all the triangles basically that touch that edge. So that's where we have to expand this to in order to compute this error. So this is the error estimates for the Clément interpolant for functions that are not even continuous. They're only H01 functions. And the proof of this is beyond the scope of this lecture series. So I'll refer you to this book by Verfurth from 2013 or the book by Bress from 2007. This one I'm not sure I put in the on our Canvas site, but this one is on the Canvas site, this book by Bress. Okay, so we've almost all the machinery that we need in order to define the in order to figure out how to compute an error estimate, which is actually uh, fully computable, or at least mostly computable. Now, suppose that our UH is in our finite element space. So this function then doesn't make sense. If we take the second derivative of UH, that's a nonsensical object, right? Because this thing is in H1, but it's not in H2, so I can't take the Laplacian of that object. So while this doesn't make sense on a global scale as an L2 function, this function does make sense. So what I mean by this is we're taking this function here, so that's either going to be piecewise linear or piecewise quadratic, and I'm computing the Laplacian of that. So if I take a piecewise linear function and I compute the Laplacian of that, well, what do I get? I get, if I take the gradient, I'm going to get a bunch of piecewise constants. If I take the Laplacian of that, I'm just going to get zero over a triangle. Okay. Piecewise quadratic, this will come out to be something, um, should come out to be a constant, which is not necessarily zero. But otherwise, for piecewise linears, this will be zero. It's kind of um, be trivial, but at least it still does make sense. Makes perfect sense. So now, for each k in the triangulation, we need to define an object, okay, called the residual for the computed Galerkin function. And that guy, the residual, what is a residual? I think I defined this incorrectly here. It should be that way, right? So the the original thing that we were looking for is this object here, right? And so if I look at the residual is going to be, you just take this object to the other side, and that's going to be f minus a minus Laplacian u, which becomes a plus. Okay, so yeah, I did have the error or the sign incorrect. I wanted to have a plus here. Okay, so I can define this object. If you tell me what is this thing you're computing, or that if you tell me what the Galerkin approximation is, I can compute its Laplacian on every triangle. And I should actually say that, right? Maybe that's also computed on the triangle. And of course, f is computed on the triangle, just on the triangle. So you're looking at the restriction of f to the triangle here. This means you're just going to restrict to the triangle, and then you're going to take its Laplacian. That's just going to be a linear function or a quadratic function. So with Laplacian, you can compute. Now, for every edge in the edge set, the interior edge set, I'm also going to compute what's called a jump residual or a derivative type residual. And so that is defined as this jump. So this is a standard notation for a jump, and it is given right here. I need the jump in the normal derivative. How do I know the normal derivative has a jump? Well, again, these are globally continuous functions. So the first derivatives exist globally, but as I go across element edges, okay, as I go from one triangle to another, there's a jump in the normal derivative along an edge. Okay, and that is precisely defined this way. So suppose I have an edge and I have two triangles, K1, K plus, K minus. All right. Actually, I'm gonna change the notation here a little bit. I was just thinking about this earlier, and I like K1 and K2 better. Although I just which one was it? K plus, yeah, K1, K2. Okay. Okay. So suppose I have an edge and it's shared by these two triangles, K1 and K2. I'm going to define a normal for that edge. I have to pick one of two choices. So either I take the normal going into K2 or I take the normal going into K1. So which one do I use to choose this? Well, the way I can do it is these triangles have a certain numbering. So whenever I generate my mesh, the triangles are numbered in a certain order. Okay, so I'm going to pick um, the edge normal to be the direction pointing into K2 with the following understanding. Okay, the number in the counting in the construction of my mesh, the number of K2 is strictly greater than the number of K1. That just means when I construct my mesh and I count these up and I enumerate these triangles, I'm going to use the I'm going to use the convention that if K2 has an enumeration in my triangle structure, which is bigger than K1, then I'm going to point the normal into K2. Okay. If this one happened to be bigger, then I would turn the normal around and go this way. You do have to pick a direction, but it's kind of arbitrary how you do it. And one easy way to do it is just use the enumeration of the two triangles. So then what I do is I compute the gradient in K1 and I compute the gradient in K2 and I subtract those two. That gives me a vector. Then I'm going to dot that with that normal NE. Okay. And so that gives me this object, which I'm going to call the jump in the normal derivative. Again, how I choose this guy is entirely arbitrary. I just have to pick a way of doing it and then stick with that. And the way I'm going to do it is I'm going to say that that normal points in this way or points towards K2 if the enumeration of K2 in my triangulation is bigger than the enumeration of K1. All right, so RK is what is called the element residual. That's because it's computed on each of the triangular elements. And this object here is what we call an edge residual. So this kind of measures how much error that I'm generating in a triangle, and this number here tells me how much error I'm generating across an edge. Both of these are computable objects. If you tell me what your finite element solution is, I can compute this, and I can also compute this using this formula. Okay. Now, that doesn't necessarily say that they're easy to compute, but they are computable. All right. And now I'm ready to define my error estimators. Okay. So for each triangle in my mesh, the residual error estimator on K is defined in the following way. So this, my notation here is eta, not n. It's eta k r, eta sub k sub r, is equal to a square root of a sum of two things. The first thing in the sum is hk squared, so that's the size of the triangle. It's the largest edge in the triangle squared. Then I'm going to square the norm, the L2 norm of the element residual. Okay, that's that guy. Again, this is computable. And the L2 norm of that, not easy to compute because I have to compute I have to actually do an integral, but it may not be too hard. It depends on how hard it is to compute that F, I suppose. This object here is going to be a piecewise, it's either going to be zero or piecewise constant. So I can compute that. And then I'm going to take 1/2 the sum over all the edges in the triangle. So this is a kind of an abusive notation here, an edge being an element of the boundary, but I think you know what I mean. It's one of the edges of my triangle. Um, so we're taking the three edges of the triangle, summing them up, right? So there's three edges. We're going to multiply by the size of that or the length of that edge times the L2 norm of that residual, the edge residual error. Okay. L2 norm squared. So you add those two things up, and then we take the square root. That gives us this object, which we call the residual error estimator. And sometimes this object is also going to be useful to us. It's just if I take all of these residual error estimators and I square them, sum them up over all the triangles, and then take the square root, that gives me this object here. So this is what's called the composite error estimator. All right, so before I get on to the main theorem of the day, which is this guy here, I'm going to take a little break and see if you guys have any questions. We may not get through all of this proof, but let's not worry about that. Let's take a little break and I'll answer your questions and you can turn your cameras back on. All right, so as I said, our goal is to state and prove this theorem 26.8. And we'll see how far we get. Um, so again, we're going to assume that we have a shape regular triangulation of a polygonal domain. We're not working on any kind of exotic domains here. We're going to assume that we have a shape regular mesh with a shape regularity parameter called kappa. Remember, for each triangle in the mesh, we always have the length of the longest edge is bigger than the radius or the diameter of the inscribed circle, right? So that's the radius of inscribed circle. This guy, for shape regular mesh, we can assume is bigger than the size of the triangle times some factor kappa, which is greater than one. Okay. It can never be equal to one. This guy is not going to be bigger than or equal to kappa, but it could be like bigger than a half of kappa, in which case kappa would be equal to two. Okay. So that's what we have for shape regular meshes. This is independent of the number or which triangle you have in the triangulation, and it should also be independent of H. That is where you are in this family of triangulations. Then there exists a constant such that the true error in the H1 norm is less than a constant times the computable error eta r. And the computable error is this object right here. Right? So this object then will tell us how big of an error we're making in a global sense or in a global sense when we're computing our finite element solution. So this gives us something very useful, something concrete. And by the way, there's also useful ways that we can estimate the size of this constant C. By the way, it depends on the shape of our domain and the size of that kappa parameter. And this kappa parameter, if we're using a uniform mesh, is easily computable. You can tell what, and you have a nice regular mesh, you can tell what the kappa parameter is. And then it's not too hard also to get this parameter. And so there are ways of computing this for very simple meshes and very simple domains, but more generally for a complicated domain, it's a little bit hard to figure out what that is without computational techniques. This estimate here, 26.10, is what's called a reliability, or it's called the reliability of the error estimator. And it's how good is this global error at telling you how big this error is? Well, it's reliable with a reliability coefficient of C. All right, so how do we prove this? Well, we need to start with this object. We need some way of looking at this object here on the left. So, how can we do that? Actually, I think I have a typo there. I think that should just be that. There we go. Okay, I think that should just be the semi-norm. Okay, So let's start out with that semi-norm, which is the same as the H01 norm. And just like we proved in the homework exercise, um, this is equal to the supremum of this inner product, okay, taken over all W in H01 with H1 semi-norm equal to 1. So we proved this when I was talking about that homework 8 problem 2. The only difference is we had this guy on the bottom. Okay, but if I set that equal to 1, it goes away and it's the same idea. All right, so this is a way of getting the norm through a supremum process of this bilinear form. Now what I'm going to do is define a linear functional on H01. The linear functional, I like this notation, LW, is just going to be equal to A inner product. This is the A symmetric bilinear form, which is an inner product, uh, where I take the first object to be the error and the second object to be that W. Okay, so does this give us a bounded linear functional? It's pretty easy to show that it's linear. Okay, if I make a linear combination of objects for the second location, then I get a linearity, and it's also bounded. In fact, I can compute very tightly what is the size of the H1 seminorm of L. The way that's done is you just use the operator norm. This is by definition the operator norm of L. There's the definition of L, just slap it in there. All right. But I just showed that that object is exactly equal to this. Okay. So that says that this H1 or this operator norm, H minus 1, is exactly equal to this H1 seminorm of the error. Okay. So what we're going to do first is look at this bounded linear functional with a simple W over there. Then I'm going to change that in a moment to something else. So let W be an arbitrary element from H01. Okay, so L of W by definition is this. And by definition, this is equal to two objects, right? So this is equal to AUW. W is an H01. Okay, it's not a finite element function. And then the second is minus AUHWH. So what I'm going to do with the second part is I'm going to compute this one. I'm just going to simply replace by what it is. That's just going to be FW. So that's that one. And this one I'm going to keep in its usual form, but I'm going to break it up into triangles. Okay. So this, of course, is the L2 inner product of the gradient UH and the gradient of W. But I'm going to then write that. That's an integral, of course. And I'm going to write that integral by summing over the triangles in the mesh. Okay. So simple replacement there. What about the next step? Well, the next step, I'm going to keep this object as is, but I'm going to take this one and I'm going to use integration by parts. I want to take um, this gradient and I'm going to throw it over onto that guy. But I'm going to do this element by element. Okay, so I'm allowed to do that. This is a smooth function if I simply restrict myself to each k. And in that case, I'm not going to incur any problems. So if we do integration by parts, I get the, I throw the derivative onto this side, I get a minus sign, and then I also have a boundary term, right? The boundary is what? It's all the edges in, and I want to stay consistent and use that abusive notation. The boundary term is all the edges in the boundary, and I have a term which looks like this. Okay, this is the outward pointing unit normal on the whole triangle. It's not necessarily equal to NE, the unit normal for the edge that I picked earlier. That depends on how I define um, how I count the triangles in my mesh. All right, so I get this term over K, but also have this term over the boundary as well. This boundary term does not go away. Okay, there's no, this guy is not necessarily zero on the boundary, so I have to account for it. This term now can be combined with this term. I can also break this integral up over each triangle. Right now, this is over the global domain, but I can break it up over triangles and I get this term when I do that. So that accounts for the first two. What about the second two? Now, once I account for uh, whether or not this guy is equal to NE or minus NE, and it can only be one. This guy can, for each edge, it can only be equal to NE or minus NE. That accounts for this jump in the normal derivatives. Okay, so I'm gonna leave that as an exercise for you to show that this term converts into this term. This term is taken over all edges in each triangle, but then this term converts the sum to all edges in the interior edge set. Okay, so that's the first part. That's exactly equal to that. Now I'm going to use fundamental Galerkin orthogonality. Fundamental Galerkin orthogonality says that if I have this object over here appearing in the finite dimensional space, this is the Clément interpolant of W. W is itself a infinite dimensional function in H01, but this function here is in the finite element space. That means against the error, this guy is zero. So when I add this term in against that in the A and in product, that is basically zero. So it doesn't even appear. But notice that this calculation held for all W in H01. This is also in H01. So then all I have to do is replace this object here with that object, that difference. Okay. This object here is what? That's my RK residual, and this is the RE residual. Okay. I should have written it that way. Let's see. This guy here should have just been written as RE, right? All right. Now what are we going to do? This is the Clément interpolant, right? So let's apply Cauchy-Schwarz and then apply the error estimates for my Clément interpolant. Okay, using Cauchy-Schwarz inequality, you're just going to break up these guys individually. Okay, when I do that, I get the L2 norm of RK and I get the L2 norm of the error over each K. And the same thing at the boundary. I'm going to get an L2 norm of the edge residual and an L2 norm of the error in the Clément interpolant. That's just Cauchy-Schwarz. Now I'm going to apply my estimates for my Clément interpolant. Remember, those estimates were a little bit weird. They involved beefing up the size of the domain from K to omega K, omega tilde K, and beefing up or expanding the edge to omega tilde edge. Okay, but both of them were H1 seminorms. Okay, and the constants that we're getting and the sizes of the H's are coming along with those error estimates. The constants I can bring out to the front because those constants were completely independent of the triangle that I was working on. Now I'm going to use shape regularity. So this one is the best I can say for this one is I'm going to leave this as an exercise to you. Why I can convert using shape regularity this H1 seminorm to this H1 seminorm over K. The reason is because if I have a shape regular mesh, then I'm over counting with this when I sum on K, but I'm not over counting by an infinite amount. The amount that I over count is only going to be like 6, okay? Maximum. And so I can replace this with like six times that and six times that. Okay, so once I do that, then I'm starting to look at something which looks a lot like the error estimator that I had. So now all I have to do is one conversion of this using a Cauchy-Schwarz inequality. And the Cauchy-Schwarz inequality I'm going to have or going to use here is the finite dimensional Cauchy-Schwarz. Okay, it's the Cauchy-Schwarz inequality that says um, A dot B is less than or equal to uh, 2 norm of A, 2 norm of B. So that's the Cauchy-Schwarz inequality I'm going to use. That's the Cauchy-Schwarz for just plain old vectors. If I do that, then the thing that pops out is precisely what I wanted, okay? This object here. Now, this object here is my element-wise error estimator, but I still want this to be the global error estimator. So how do I do that? It's going to be one more application of the discrete Cauchy-Schwarz inequality. Again, I'm going to leave that as an exercise for you to show how this is just a sum over a finite number of things. And I've got an object here. It's really looking like that object again. So that's what I mean by applying the discrete Cauchy-Schwarz inequality again. Once I do that, I get that. Finally, um, now just divide both sides by this object here. Okay. And that gives me this estimate for this quotient. This object here now is the global error estimator. So we're very close now. Once I take, so this holds for all W, so I can take the supremum on this side. What do I get when I take the supremum? I get the operator norm. So the operator norm has to be less than this object, keeping in mind that this is an upper bound, and when I take the supremum, I'm going to get the least upper bound. But we showed earlier at the very beginning that that operator norm is equal to the H1 seminorm of the error, and that gives us the result that we want. Okay, so I apologize. I took a few minutes overtime. I'm going to let you read the rest of this here, and I'm going to write a few other notes. But the reason why I was trying to motor through this is I thought, well, if I can get through it, then we don't have to meet again for another class. So that's what I think I'm going to do. I'm going to give you this. I'll write a little bit more. So rather than having a full um, uh, lecture 27, I'm just going to write another page maybe of this guy. I'll add on to that. And the next error estimate that you want to prove is this one. And I'm going to explain why this one, along with the reliability error estimate that we just proved, why that's good and why that can be used for improving the quality of your solutions. So the idea is you have a true solution, and you want to compute a Galerkin approximation of it, but you might want to improve the quality of that solution by doing what's called adaptivity or adaptive mesh refinement. So these two error indicators can be used for that. I'll write up a couple notes and I'll put those online for you guys on Canvas and you can have a look at them. And so I think maybe it's good that we just leave it there and we don't have to meet at the final exam time like I had considered doing. And yeah, I hope that you get something out of that, um, uh, those notes, but I'll leave it to you on to go through them on your own. Okay, so with that, I'll end the class. This will be our last class, and I'm going to end the course there and take your questions.